name is Amy Merkel. I'm a research scientist at LASP and I'm a manager in LASP Office of Communications. It is my pleasure to introduce you to our speaker this evening, Dr. Amal Chandran. So Amal, you can, there you go. So Dr. Chandran is a project manager at LASP and an adjunct professor in the Aerospace Engineering Department at CU Boulder. He also holds a joint faculty appointment as an assistant professor at the School of Electrical Engineering at Nanyang Technological University in Singapore. He's the director for space technology at the Satellite Research Center at the same university in Singapore, where he's developing new satellite missions to train space scientists and engineers. Dr. Chandran received his PhD from CU Boulder's Aerospace Engineering Department in 2010 and spent his postdoc years at the National Center for Atmospheric Research in partnership with the University of Alaska before returning to LASP in 2015. This evening, Dr. Chandran will talk about CU's INSPIRE program, an acronym that stands for International Satellite Program in Research and Education. He'll discuss this program's novel concept, its hands-on training methods for students, and the upcoming launch of INSPIRESat-1. Thank you so much, Dr. Chandran, for joining us this evening. I'll now turn the presentation over to you.
Thank you very much, Amy. Can you see my screen?
Yep, we see it.
All right. So as Amy mentioned, I'm a program manager at LASP and an assistant professor at the Nanyang Technological University in Singapore. And this dual faculty appointment itself was kind of the result of the work that we started doing at LASP in trying to put together a space university consortium in 2015. So this started over coffee with the ex-engineering director of LASP, Mr. Mike McGrath. So Mike and me had a coffee one day and we were thinking that, we've been extremely successful in teaching spacecraft design and getting students involved in our various space missions at LASP. And talked a bit about my background and where I was from and how space capacity building was quite lacking in many parts of the world and how it would be good if we could collaborate internationally on student space missions. And that kind of set the idea for this whole program. What you see on the screen are the various missions under the INSPIRE umbrella that we have right now. We have about 7 missions, and I'll talk about most of them in this lecture. So as I mentioned, I grew up in a place called Trivandrum in the south of India, so about 8 degrees north of the equator. And it's actually on the magnetic equator, or it was on the magnetic equator. So that made it a very interesting place to study ionospheric bubbles and the equatorial plasma jet and features like that. So India set up an equatorial station with a sounding rocket program over there. So, and in this slide, I have pictures of the sounding rocket going up from the tropical region, and they shoot it out over to the Arabian Sea out west. And in the start of the program, you had people carrying rocket heads on bicycles, and instead of an anechoic chamber to test EMI interference, the satellites used to be put on bullock carts. So it was very basic at that time. My college, my university, engineering college, was right next to the Space Center. So every Wednesday we would see sounding rocket blast off. So I had an interest in space, and once I finished my undergraduate degree, I went to Virginia Tech to do a master's in aerospace, and following that, I came to CU Boulder to do a PhD in space science. Following this, I worked at the University of Alaska and NCAR as a postdoc from 2010 to 14, and came back to LASP in 2014. So while at CU Boulder, I worked as a graduate student on the aeronomy of ice in the mesosphere satellite. My PhD thesis was looking at waves in the mesosphere region, so at a region of about 85 kilometers in the atmosphere. So my research area is mostly focused on the neutral atmosphere, mesosphere, lower mesosphere, thermosphere, and ionosphere coupling. And in the various INSPIRE missions, you'll see that that theme has been adopted because, I've been the PI pushing most of the science on these missions. And I work with collaborators along those lines. So one of my objectives is to get more PIs and broaden the science that we do through these INSPIRE missions. So as I mentioned, during my PhD studies between 2005 to 2010 at CU Boulder, I was part of the Colorado Student Space Weather Experiment. So this was a CubeSat about the size of a shoebox. 10 centimeters by 10 centimeters and about 30 centimeters in length. So almost exactly the size of a shoe, half the size of a shoebox, I would say. We started working on a concept design for the spacecraft in spring of 2008. And what you see on the slide up here is the timeline going from 2008 to 14, and the number of students who took courses in the spring, summer, fall, and all those semesters. And I was one of the first 10 students that took this course. So it was a very interesting course. We had this objective of actually designing a satellite, which was, CubeSats were new to the field. People were not building them. This was funded by NSF. NASA thought that these were never going to work. So NASA was not funding science missions at that time. And NSF actually took the lead and funded the CSSWE spacecraft. So we built the spacecraft. I wasn't part of the build because once NSF funded it, which was around 2010, I was already out of the program. But once NSF funded it, then you can see the number of students also started going up. So this is an exact trend of what we have seen. If it's a funded project, if it's a real project, more number of students will take it because they really want to work on actual hardware, not really on concept studies. So that was a very important takeaway from this mission. We developed the spacecraft. We launched it in 2012. The spacecraft worked really well. There was a period of loss of contact, but because it was very robustly built, it came back and we were able to get a full mission out of it. And we had a fabulous, I think we had almost a 1-year mission. I think the number of papers from this is more than 20 and counting, including papers in Science and Nature. So it kind of proved that CubeSats can do quality science. And it, and I'm very glad it succeeded because NASA and a lot of other agencies jumped on the bandwagon, and now we have a lot of CubeSat science missions. So this was, my motivation for thinking, can we develop an academic program for effectively teaching spacecraft design? And can it be used for space capacity building? So if you go to other countries, even, developed countries in Europe and Japan or, Singapore, there's not much spacecraft design or education happening in universities. So universities such as the University of Colorado and what we have in the US is very unique in terms of how science and instrumentation can be done, and even full spacecraft missions can be run from a university setting. So we want to see how can we use this for capacity building. How can universities develop a sustainable CubeSat program or a SmallSat program? So very often universities would build a satellite and there would be no follow-up. That's it. That would be it, done. So, how do you retain manpower? How do you build out and retain full-time engineers that can mentor students coming in and create a sustainable program? And finally, we wanted to see if we can foster international collaboration to bring together universities to address common science objectives. So a few things we had in mind was common problems, facing mankind, like climate change, for example, or space weather forecasting. So these are all things where we could address these problems from multiple platforms. And if instead of one agency or one university or one country putting up all the resources, if the CubeSats were funded by multiple countries, can we solve these problems together? So that was one of the ideas that we had. So these were the initial thoughts. And in 2015, me and Mike McGrath went on a fact-finding trip. So we went to India because we had an invitation from the Indian Institute of Space Science and Technology, which is a university run by the Indian Space Research Organization. They had invited us to go there and give a talk about what we do at LASP. So we went there. And in Taiwan, there was a space science, there was the National Central University, and they had hired a young faculty at that time who was a recent graduate from CU Boulder. and he was trying to put up a space institute. So he had also invited us to and said, look, if you could come and give a talk, that'll be great. So we were going to do that. And in between, we had a layover in Singapore, and we found that Nanyang Technological University had a satellite center that was building satellites, and apparently it was like a mini LASP. So we wanted to go and see that facility as well. So we did, and we have pictures here where we are talking to people building a lunar lander. Subsequently, the lunar lander crashed. This was a mock-up of the lunar lander. It did make it to the moon. It orbited, and then on the final approach, it crashed, I think a couple of years back. And I think India is building a second lunar lander. And then this was, the spacecraft is at Taiwan, where the National Space Research and NSPO, the National Space Organization, works with NOAA in the US to build the cosmic satellites. So this was, I think, a mock-up of cosmic or a Formosat satellite. And then the professor, the director in charge of the Satellite Research Center, explaining to Mike the various missions he does. So after this, we came back with, it was a resounding success. The mission, the fact-finding trip was a resounding success. We got interest from people saying, look, if you take the lead and put together a curriculum, we will be, we will love to get involved. So the idea we had was that each participating institute brings in resources. So no one partner gets burdened with the full cost of the mission. And partners get to share each other's resources to develop new technologies and capabilities. The project selection will be based on discussion with the institutes. We wanted to give young scientists and engineers to be first-time PIs and PMs. Those are very hard to get by in this industry. So we wanted to be able to train principal investigators and program managers. And the project will build capabilities at the participating institutes, and it'll be a cross-cultural experience for students. So we started working on Slack and Zoom a lot more than other people did. So universities joining the consortium had different goals. So, and we did not discriminate between anyone to join. Right now, we are kind of capped at about 12 universities because we can't find enough work for everyone to do. And it's becoming too big to manage. But, hopefully that will change in the future. The participating universities are at the bottom of the slide. You can see LASP, the Indian Institute of Science and Technology, National Central University in Taiwan, NTU from Singapore, University of Versailles from France, University of Alberta, Canada, the University of Iowa, Fong-Sendrum Jülich, that is associated with University of Wuppertal in Germany, Sultan Qaboos University in Oman, and QTech in Japan. So everyone had a different goal. So for the Sultan Qaboos University in Oman, it was to initiate a space program and start teaching courses related to space. They had absolutely no space capabilities. Universities like NCU, Alberta, Canada, IAST, Iowa have some facilities for hardware development and personnel for teaching, but they wanted to get, they wanted to be building full spacecraft. They wanted to be building full instruments and operating missions, which was where NTU Singapore, LATMOS in France, Jülich in Germany, and QTech were. And then we have LASP, which was kind of more advanced than all of these universities. But the goal was to be a global leader in space education and develop curriculum for teaching spacecraft design. So in next few slides, I'll just briefly mention the missions. I won't bore you with details on this, but I'll just talk about the different configurations of the spacecraft. So INSPIRESat-1 was our flagship mission. We started working on it sometime early 2018. It is ready for launch now. We've delivered the spacecraft to the Indian Space Research Organization and IAST, and they are going to be launching the spacecraft. And we are awaiting launch. The primary on the launch is a little bit delayed, but we expect it will go up in December 2021. It has two payloads. It has a payload from Taiwan, which is a plasma payload looking at ionospheric plasma in situ. And then we have a solar X-ray spectrometer that has been built at LASP and funded by NASA. INSPIRESat-2 has already launched. So it started later, but they were able to get a launch in January 2021, and they launched. And the mission's been a success, and it's operational, though it has had some anomalies recently. It's in a sun-synchronous orbit. It's designed for about 1 year in LEO, so it's coming to the end of its life right now. And it has the compact Ionosphere Probe from Taiwan as its payload. So if you look at the two spacecraft, you'll see this is about this is the INSPIRESat-2 is a 3U spacecraft. It has only the compact ionosphere payload. This is about a 12U, so it's roughly 4 times the size of INSPIRESat-2, INSPIRESat-1. INSPIRESat-3, we started working on it around the concept in 2019. We just got funding from NASA for the instrument onboarded about, I think, a couple of months back. So work on the spacecraft will start very soon, and we expect to launch in 2024. Compared to INSPIRESat-1, which is 12U, and INSPIRESat-2, which is 3U, this is a 27U. So it's a much bigger, bigger spacecraft. And it has a UV instrument, an imager for imaging the thermosphere, a magnetometer for looking at magnetic field around the aurora, and an interferometer for looking at the mesosphere gravity waves and temperature, mesosphere temperature, basically. INSPIRESat-4 has an electric propulsion on board to actively deorbit the spacecraft. And that one is almost ready. It's been built and in Singapore and ready for launch in September 22. So in this presentation, I'll talk in detail about INSPIRE 1 and 4. INSPIRESat-5 was a French satellite. It's also launched already. It's a small 1U spacecraft, so quite small. And it launched in January 2021. It's still working. It's had a great mission so far. And I mean, the French were able to build it really fast. All of us, participated as well. INSPIRE 6 is a spacecraft funded out of Taiwan and expected to launch in 2024. So what's been common across all of these is that we've developed technologies that are common, and we've shared them. It's in the open domain. We publish all of the details. That's one of the facets of the program, that nothing is restricted or nothing is what we call ITAR constraint. All of the technologies that we have developed is in the open domain, and we use the fundamental research exemption because it's all for science missions. So I'll talk a little bit about the INSPIRESat-1 spacecraft. The size of the spacecraft is about 30 centimeters by 20 centimeters by 15 centimeters. And it's a ring deployed spacecraft. So most CubeSats go inside a box, as you could see from the INSPIRESat-2 pictures. And then a spring pushes it out. The lid of the box opens up, and the spring pushes it off. With this one, it's on a ring, and the ring separates from the spacecraft mounting port, and then the spacecraft gets deployed. All of the tests have been completed, and we have delivered the spacecraft to our partner university in India in June. And they've completed their testing with their ground stations, and we expect to launch anytime. We've been ready for launch since July of this year. So I'd like to play a video showing the concept of operations of the spacecraft. So these are the multiple ground stations we have, and you have contact and in nighttime, we will be operating the plasma payload, and the other spacecraft you saw was INSPIRESat-2. So daytime, we're looking at the sun and making X-ray measurements of the sun. And again, at nighttime, we're making plasma measurements. We don't make daytime measurements of the plasma because when the sun is active, there's too much plasma and the instrument gets saturated, and we can't really separate out the finer features that we're looking for. So we're looking at plasma bubbles and ionospheric density variations at the nighttime ionosphere. So how does a program like this work? Because you have contributions from the multiple universities, you have faculty working in the multiple universities, you have students from the multiple universities. So this is what we, it's a rough sketch of how INSPIRESat-1 came about. The spacecraft has contributions mainly from Taiwan, India, and US. So we have LASP, NCU, and IAST contributing. LASP did the structure and thermal. The attitude control determination was done by LASP. Most of the flight software was done by LASP. The DAX instrument, the dual aperture X-ray solar spectrometer, was also built at LASP. The onboard computer board was built by the Indian University. The COM and the power board. The power board ended up being a development of multiple universities because we had trouble with the power board, and finally we had inputs from everybody, and we ended up finishing it off. The Ionosphere Probe was built by Taiwan, and the COM board was also LASP, NTU, and NCU. The spacecraft integration and testing happened at LASP. The launch vehicle integration and testing will happen in India, and IAST is taking care of that. And the launch is from the Indian Space Research Organization. And for operations of the spacecraft, all 4 universities that are involved, all 4 of these universities will be actively involved. So it's been a challenge managing the project. So we had principal investigators at all the 3 primary universities in the US, India, and Taiwan. We had student program managers and student systems engineers, and we had subsystem leads that were from different countries as well. So every summer, the students would come to Boulder from these universities, and they would work together to build the spacecraft. So that's how we ended up building it. But one of the main problems was student retention and continuity, and all the students in red in these who started off on the project have left. But thankfully, the PIs are still there, and we were able to put together the spacecraft. So I'll just very briefly talk about the instruments we have. The Ionosphere Probe, the compact Ionosphere Probe, has 4 instruments. It can be operated in 4 modes. We have a Langmuir probe that measures the ionospheric electron density. Then we have a retarding potential analyzer, which is essentially a set of 4 grids to which we send power, and we can sweep the voltages. And by changing the voltage, we can look at the ion that gets past the negative and positively charged grids, and it sort of acts as a spectrometer, and we can find things like ion density, ion drift velocity, because we have 4 ammeters on the instrument, so we can measure the arrival angle based on which of the 4 grids the current comes from when an ion hits it. And by looking at by again changing the voltage, we can look at what the spacecraft voltage is, and from the Langmuir probe we know what the electron temperature is, because to measure electron temperature, the electrons have to go, the velocity of the electrons which is related to the temperature, have to be above a certain value for us to measure it. So we can get the electron temperature and ion temperature from that. And by sweeping the voltages, we can get the ion composition. So it can be run in many different ways, and essentially we can get the ion density, composition, and temperature in the ionosphere. So an instrument similar to this is already flying on a satellite called FormosaSat-5, but it's at an altitude of 800 kilometers. So the density of the ions drops exponentially with altitude. So we hope to be in a lower altitude at around 400, 450 kilometers and sample a much higher density of ions at our altitudes. The second instrument we have, the principal investigator, is Dr. Tom Woods at LASP. It looks at the plasma, it looks at the flares in the solar corona in soft X-rays, and it's a spectrometer. So it looks at the spectrum of the X-rays, and by looking at the emission lines for iron, silicon, magnesium, sulfur, we can look at the abundances of these elements in the solar corona. So this is a follow-up to the miniature X-ray solar spectrometer that James Mason talked about probably I think last month. And we are hoping to get really good data from DAX in the coming months. So complementary missions to IS-1. So as I mentioned, we look at ionospheric plasma. To kind of characterize the whole ionospheric density, you want multi-point measurements at different altitudes as well, because we want to see how ionospheric disturbances and plasma changes happen. Why is it important? An example is for communication, or even GPS. As signals pass through the ionosphere, they get scintillated. So if we know the plasma density, and we can use that for nowcasting and forecasting plasma bubbles and density variations, that we can help with looking at ionospheric communication, ionospheric effects on VHF, UHF communication, as well as GPS signal scintillations. So you really want to be looking at the ionosphere with a constellation of satellites to be able to characterize this. So INSPIRESat-2 carries the same instrument, and INSPIRESat-4 also carries the same instrument. Unfortunately, because INSPIRESat-2 launched in January and now we are launching end of December, we feel that the overlap will be minimal. It would have been great if we launched 4 months ago, but that's water under the bridge, so we can't. FormosaSat-5 is at an 800-kilometer orbit and it's operational, but so it'll give us information from sun synchronous orbit at a higher altitude. And INSPIRESat-4 is at an equatorial orbit, so it goes around the equator and at an orbit that, and at an altitude that will go from 400 to 250 kilometers. So we should get some great data from that as well. And then the MINX missions 1 and 2 flew the solar X-ray spectrometer. Those missions have ended, but DAX will complement and extend those observation record from those missions. So now I'd like to talk about the fun stuff, the spacecraft. So as I mentioned, the spacecraft bus is developed in the open domain, and all the participating countries have access to these developed technologies. The onboard computers, power system, flight software, structure have all been custom developed for our missions. We have bought ADCS and radios from commercial off-the-shelf vendors to put in these spacecraft. So we've also made the subsystems that we have developed to be compatible with the CubeSat form factor, so it is easy to scale, and we can put it on custom structures and get deployed from rings from launch vehicles, and we are not constrained by the CubeSat standard here. So I have a few pictures here. This is the flight INT of the spacecraft. You can see the spacecraft structure, which is aluminum 6061, and the plasma payload being put inside. It's an extremely sensitive instrument with 4 very, very fragile grids on the top, and it's very easy to tear them. We already tore them once. So some pictures from the testing. This is the satellite on the vibe table. This is the one inside a clean acrylic case for end-to-end testing with the ground station, and this is on an air-bearing table where we rotate the spacecraft. And I'll be able to show some videos here. So in the first video, you'll notice the deployment of the solar panels and the antenna, so which is very critical. What we did here was we took it to 36. So the float over as you approach Boulder on 36 West. And then from there, we have line of sight with the LASP ground station, and we send a command to the spacecraft. So it's about, I would say, maybe couple of miles or more. And then we send a command to the spacecraft to deploy the solar panels and the antenna. So one of the most important things, as you can imagine, is the deployment of the panels and the antenna, without which, it's an end of mission. So please watch for it.
There it is.
Yeah. So in space, it would deploy completely. Because of gravity, it is keeping the solar panels down, but it would deploy completely all the way, because we have 270-degree springs and a stopper to make it stop here. So, and what you see here, the red tag cover is the cover for the solar telescope. And this one, you can see the spacecraft spinning around.
Looks like it's on sale. Buy a brand new satellite. Yeah, right.
So this is the ring on the spacecraft. So this is the one that mounts onto the rocket. And I don't know if you could hear the video, but the students are saying, looks like it's on sale, and come down and buy a brand new spacecraft. And this is a video of the spacecraft where we do a solar pointing test. So we have facility at LASP where we have a set of mirrors that take the sun, it tracks the sun and brings the sunlight inside. And what basically the satellite is trying to do is find the sun and point to the sun. So we use this to make sure that the facing is right and the satellite is turning the right way. It's very important to make sure that it's pointing the right way. It can find the sun and orient itself. So If it can do that, it can charge the battery and it will be what we call power positive, in which case we can send a command and get it to work. So one of the most important steps. So it takes some time. I'm going to skip through the video, but this is not the right phase. So what the spacecraft does is it will slowly, very slowly, because the wheels, the reaction wheels that are used to produce torque and turn the satellite are quite small, and it's on a heavy table. So it takes quite a bit of time for it to turn the spacecraft. But it does, it eventually does. And once it points to the sun, it'll stop and hold its position, which is what we want to do, what we want to see. So and an interesting thing here to note is that we are commanding the spacecraft over the radio at this time. So the spacecraft is flying, is being tested as we would fly it. There is no hardline connection. The spacecraft's on an air-bearing table. So we, compress the air, lifts the table, and then the reaction wheels can turn the spacecraft and point it to where it needs to point. So, all right. So after this, we also tested inside a vacuum chamber where we pump out the air and keep the spacecraft in vacuum and cycle it through temperatures, the hot as it sees the sun and the cold as it's in eclipse, and verify that all the components of the spacecraft are operational. So that's what you see here. And current status of the spacecraft, it is at the Indian Institute of Science and Technology, and launch is on board the PSLV rocket. It's a really big rocket. And we expect it to fly sometime in December 2021. Okay, so I'll talk about the next mission and my adventures in Singapore. So once we were doing this, Singapore contacted me and said, could you please come down and start an education program over there? So I took that up, and since 2017, I've had a dual faculty position, and we've been working on a few satellite missions over there. NTU, this is one of their iconic buildings. It's like a number of this is a building on campus where a number of it's like a number of dumpling boxes stacked up on top of each other. But yeah, so the Satellite Research Center there has worked on a number of missions before. They built 100-kilogram spacecraft. They built 6Us, 2Us, but it's all been technology focused. It's not been space science mission. So one of the agendas of me going over there was to drive some science missions. So in next year, we have 4 missions lined up. We have 2 3U spacecraft and 2 27U spacecraft. And I've been leading development of the 27U and the 2 3U spacecraft. So the 27U we are building is looking at, again, ionosphere and neutral atmosphere coupling. So it's got an infrared imager that's looking at atomic oxygen emission in the mesosphere and thermosphere, and we are getting, we'll be looking at neutral temperatures and using that to detect gravity wave propagation up into the ionosphere, and which the gravity waves can be from tropical thunderstorms, and it's going to address this question of how do waves propagate up from the tropics, and hopefully we can get some pieces of the solution there. And we also have the plasma payload, which will look at the plasma. So what we are trying to look at is a question where in the ionosphere, scientists have discovered this 4-peak structure, and people attribute the 4-peak structure to gravity waves and waves propagating up from below. So hopefully we'll be able to see, because we are flying along the equator, right along this region in the equator, we'll be seeing the 4-peak structure, and hopefully we'll be seeing wave correlation or something similar. I don't know. So we are excited to see. So one of the interesting things we are doing is we get deployed into a 530 by 450 kilometer orbit, and then we use propulsion to bring the orbit down. And then finally, at the end of mission, we use propulsion to stay in orbit. So the idea is to come down to about 350 kilometers and then use our propulsion to stay there. So it's quite exciting to do that on a CubeSat because it's not been done for orbit maintenance at that altitude. So we are trying something new. For our primary science mission, we won't be firing the thruster. We'll just be running the instruments. That's what the satellite looks like. It's pretty big compared to INSPIRESat-1. We're packing a lot of things in it. And the assembly of the spacecraft. So I actually have a video that shows this better, but here, this is what we call a flat sat where all the components are laid out. And then we are integrating it into the spacecraft. So compared to INSPIRESat-1, this is fairly larger sized, and I think you will enjoy this assembly video. So the main thing you see here, this is the thruster. It's a Hall effect thruster, an electric propulsion thruster with iodine. And that's the avionics stack, which uses the power board, the onboard computer getting assembled. And that's the infrared imager that's going up on top. So finally, we put all the solar panels on. So you'll notice that this doesn't have the cells on it. And that's because this is an engineering model. It's not the final spacecraft. So we did all the testing with this, and now we are ready to assemble the final spacecraft here. So one of the tests we do is called a shock test, where we subject it to a high shock load to make sure that the structure is robust, and you can see that here.
Starting shock test. Starting shock test.
So that was the shock, and nothing fell apart. So that's a good sign. So again, coming back to INSPIRESat-1, it was mainly built through a 10-week summer program at Boulder in 2017, 18, and 19. We had a number of students come over. The students, it's a cultural experience for the students as well to work together, to bring what they've been working individually and then work together. Then we have a review at the end of the summer. They go back and work on stuff again, come back, and we build it. Of course, during 2020, when none of the students could come, the professional at LASP helped immensely to finally put the spacecraft together and finish it off. And it's the same in NTU as well. We have professional support as well for building IS-4, but the students do bulk of the work on these projects. It's been a great learning experience. They've won a lot of contests, and I really like this picture because we have a CU Boulder student, IIST student, and we have a NCU Taiwan student, and they all three went to Rome, presented the mission, and they got first place in the IAA mission idea contest in 2017 and 2018. So that was a great moment. In Singapore, we have student satellite series that are going on. I'm teaching graduate and undergraduate courses at NTU. And we're building 2 student satellites as well. So these are 2 3U satellites that we are building at Singapore, and they're going up next year. So these are about this size. So, and we have a deployment test video.
Just wait for 10 seconds and we'll stop. 10 seconds. Deploy. Oh my God.
So engineers get excited when they see the antenna deploying, but it's at extremely cold conditions, -20 degrees. If we want to make sure that the battery is charged enough to deploy, this is one of the major tests that we do to make sure that at 20 degrees, at a very cold temperature, the battery can produce enough current to deploy the spacecraft. We've had a number of students that we have trained, PhDs and master students at CU and other universities. through this program. Every year we try to have a workshop. 2016, it was in Taiwan. A lot of night markets, apart from 3 days of intense presentations. 2018, we had it in Boulder. 2017 in Boulder. 2018 was in Paris. 2020 January, we actually had it in India before the lockdown happened. So in summary, I would say that INSPIRE has built new partnership. We've initiated student exchange programs. We found new avenues for access to space. We never thought a LASP-built spacecraft would fly on an Indian rocket. So that's happening. And NASA just funded a new instrument to fly on another one. So that's been a really big positive thing that's come out of it. The cooperation between universities facilitating those kind of exchanges. A small satellite platform was developed, and we have demonstrated that this can be a viable and sustained model for academic collaboration. What's next? We need new PIs to take INSPIRE forward with new missions. Merging entrepreneurship with academia. This is something that we are seeing. A lot of our students have spun off companies in Singapore, Taiwan, and India, and there is strong government support in these countries to grow their space industry as well. And we see the same interest in the US as well, that some of the technology that we have developed can be commercialize it. And it could be a win-win. I'm really thinking how we can take that forward. And partnering with entities such as the Committee for Space Research or COSPAR to grow the capacity building part. So, and we have talked with NASA about setting up a Center of Excellence at CU Boulder to keep doing this with NASA funding. So that's all I have. Thank you for your attention. I'll be happy to take any questions.
All right, thank you so much. That was a great presentation. If anybody has any questions, please put them in the Q&A. Type them in there, and we will answer them live. While people are doing that, in the meantime, I have a couple questions. So how many students? Do you have like a total number of how many students?
Yeah, it's been difficult to keep track of that, because in each university, they have a larger number of students that are involved. But every summer in Boulder, we've had about 20 to 25 students come here. And this is part of graduate projects at CU Boulder as well at aerospace. So this is a 6-credit graduate projects course. So it's pretty intense for the CU students that take it. But from India, about 4 students come. Taiwan sends about 5 or 6, and Canada has been sending 4 or 5 the last couple of years. When we had it in 18 and 19. So it adds up to about 22 students that are in at the summer program. And then individually at the universities, I would say that they have teams of about 6 to 8 or 10 students working on it.
So do they all come to Boulder?
No,
Okay.
only like 4 or 5 students, because we can't accommodate everybody.
Yeah.
So we usually try to do it so that we cover the accommodation for all the students. It was in the budget that we would cover accommodation for up to 20 students. But subsistence, monthly allowances and air tickets are usually covered by the participating universities, and we cover local accommodation. And then there is a question of space. Where do we have the students work at LASP? So we've worked with, working with CU Aerospace has been beneficial, because we can use CU labs. So we get a couple of test benches where anything that is not flight hardware can be done there. But flight hardware, we actually try and handle it in our clean rooms. But everything else kind of gets done at CU Aerospace building. So,
okay, so then I have a question about funding.
Yeah.
You showed a lot of projects. I mean, not just INSPIRE, you had Arcade, and you had
yeah,
can't remember the other one.
You can still see my slides, right?
But no, we can't see your slides anymore, but that's okay. But so do all these projects get funded through the individual governments? Is it, or is it similar to NASA?
Yeah, let me show that. Yeah, I had a slide that I put on the backup because I didn't know if people would be interested.
Sorry, I'm interested. Maybe the rest of everybody is interested.
Yeah, so this is, you can see the slide, right, Amy?
Yeah. Yes.
So this is about the total money. I think it's up to date with what we got for owls, NASA grant that we just won recently for owls. So CU Boulder kickstarted this with a $1.25 million funding. And I have to thank Russ Moore, the provost, and Phil DiStefano, the chancellor, who have been great champions for this effort. Apart from Dan Baker and Mike, who pushed it from LASP. But CU funded it, and that helped get the summer programs going and building INSPIRESat-1 spacecraft at CU. It's not much, but it's enough for a CubeSat, right? And Taiwan got funding for the payload, and India, the IAST got funding for the launch. So everybody contributed, and we were able to kickstart INSPIRESat-1. Following that, we won a NASA grant for $1 million for instrument development. And then NCU, National Central University in Taiwan, was able to really leverage INSPIRE and INSPIRESat-2 for an $8.5 million funding over 5 years. At NTU, I was able to get $4 million from them for INSPIRESat-3 and 4. And the French got about $2 million. And IAST raised 1.25, and recently, I guess we raised about 2.3 from NASA. So the bulk of the funding is overseas. It's coming from funding agencies in those countries, and not from US. So we've talked to NASA about this, about funding INSPIRE as a capacity building and international program, and having a center of excellence at LASP, maybe for CubeSat building, and taking a leadership role in space capacity building and education. NASA's interested, and we hope that they'll show some support at some times.
That's fantastic. What you've done internationally for the CubeSat program is just amazing. So congratulations on all that. We have a couple of other questions coming in. One is, have you seen the growth of satellite program sustainability through INSPIRE at any of these universities? So that kind of is a follow-on to the funding.
Yeah, I would say that NCU Taiwan and Singapore has been success story. Actually, the French LATMOS has been success stories. So LATMOS, the lab in France, launched their first CubeSat, the 1U, and they have a 2U funded, and they are pushing for a global constellation, for radiation monitoring through CubeSats with KINES, their space agency, and ESA, and they've had success over there. NCU has had the Space Institute funded. They have about 3 or 4 missions funded. So Taiwan has been a success story. NTU also got a major grant. So the VLEO, the low Earth orbit mission, INSPIRESat-4 has helped NTU get a $25 million grant for a new mission. So in these 3 countries, we've had enormous success. And I think Canada also, University of Alberta, got some money from the Canadian space agencies. So it's been a success, except in the US. I would say we've only got that. I mean, we did get 1 grant, but hopefully we'll get more.
Yeah, but it's small. I mean, it's
a little bit small.
There should be more from the US. So there's a question about when you said you wanted more PIs. So. Do you have a link or any way that our attendees can learn about those opportunities? Or
it's more about being involved with INSPIRE and finding out that if there are, for example, we've hosted instruments. So Tom Woods had DAX, money for DAX because MINGS-2 had an early termination to life, right? So he had funding left over for building an instrument, and he was looking for a platform or a spacecraft to put it on. So we were able to get that instrument on board. So we've talked with PIs before about who have leveraged IRD money to develop payloads, and if those are near flight and we have payload space inside a spacecraft, that's a perfect way to get involved, right? And then there is also the opportunity where I would say just talk to me, and then if we have payload space availability, we can always put these small instruments up. So if you have a 1U instrument concept and we want to go with that, then you can get you can look at avenues to get that built, right? Either internal research and development funding or NASA funding for instruments. So Ed Tiemann, the PI on the occultation wave limb sounding instrument, used the INSPIRE opportunity and payload space INSPIRE 3 to put to write a proposal to NASA. So that's the.
So then the next question is, as you go through managing multiple institutions, students, funding, do you see this program becoming more and more towards a well-oiled machine? And are there lessons learned for organizing these missions that will help the INSPIRESat launching in the coming years?
It's I would have thought it would become more well-oiled, but it's becoming more difficult because I've managed these projects traveling back and forth and building teams for the last 4 years, and it takes a toll on you managing it across countries. But I would say that hopefully we find a different method for doing this, because right now, the last 2 years, we've not been able to have summer programs. And individual PIs associated with the project have been writing proposals to their respective governments and funding agencies and getting in money. So we have a couple of missions in the pipeline where we are going to work together, but INSPIRE 6 and INSPIRE 7 are basically being built in their home countries. So INSPIRE 1, 2, 3, and 4 had a lot of collaborative spacecraft build. INSPIRE 3 is going to be the next flagship INSPIRE mission where everybody is going to come together to build it. 4 is almost built, 2 is in orbit, 1 is done, and 6 and 7 are being built at individual countries, right? So after 3, I would hope that we can follow this model of at least building one satellite together, while the rest of the spacecraft we support each other during reviews, preliminary design reviews and critical design reviews. The main thing holding us back is a lack of funding. If we have enough funding at LASP to support professionals and student time on it, then we would be in a better position to support all of these missions. The CU funding
is the INSPIRE program going to stop at 7, or are there going to be more INSPIRE sats, or are you moving more towards satellites that have different acronyms?
I mean, satellites do have different acronyms, but we call them the satellites in the series. For example, INSPIRESat-4's name is Arcade, Atmospheric Coupling and Dynamics Explorer. So there's different mission names for these, but it's just the satellites in the series and if we have been involved. So the Scooby and Scooby-Doo missions from Singapore are not part of the INSPIRE umbrella, even though we have leveraged quite a bit, but none of the other universities have been part of it. So we have not put them under the INSPIRE umbrella. So yeah, I think we should be having more satellites. I hope we do. But I am more keen to take this in a direction where we are working with people like COSPAR. COSPAR has an initiative for a task group. They have a task group for addressing space weather through a constellation. And they kind of want INSPIRE to provide the program management aspect of managing missions from multiple countries. So maybe that's the way forward. I don't know. But if we have more PIs, we have more champions, then it can work.
And then there's one more question about is it only graduate school credit?
It is. It's only available, and last 2 years it wasn't because we didn't run the summer program, but the summer program is only available as graduate projects for the summer term, because graduate projects exist in spring and fall, and they didn't have anything for summer. They CU Aerospace wanted INSPIRE to fulfill that gap. So yeah, unfortunately, it's only available as graduate credits.
And then what is your greatest joy that you take out of everything you've done? And what is your biggest challenge?
Nobody thought it would work. So, when we put this together, it was a long shot that it's going to be really difficult. Right. So to see it working and to see that spacecraft built and delivered, and then other spacecraft built under this umbrella has been very fulfilling. So I didn't even know if it would work, but getting this together. So there was a whole lot of problems when you start out, right? How are we going to do this with all our export controls and regulations on our side? Is the launch going to work? Are they really going to contribute a launch for the spacecraft, right? Are we really going to be able to develop systems in different countries, bring it together and make it work? So all of those were there. And are we going to get it funded? So making it come true was very, very fulfilling. And a lot of students, that was very fulfilling as well. I think there are a lot of students who have chosen space science and stuck around and chosen this career path, having worked in this program. So that's been one of the big achievements of the program as well.
Somebody wanted to know if the summer school is going to happen this summer.
This summer, I hope so. 22, yes. If travel restrictions go away and people are able to send students, I'm hoping we can have it this year. We need to start working on INSPIRE 3.
Okay, so looks like that's all for the questions. I just want to thank you again so much for doing this, and it was a great presentation, and congratulations on your amazing endeavor and success in pulling this off. I just am in awe at everything you've done. So, and it's a great cultural exercise of bringing in the world into space science. And so just congratulations and thank you so much for joining us.
Thanks, Amy. Thanks for the opportunity.